Hello everyone, my name is Priyank and I'm here today to discuss about my final project for this particular subject, which is object detection with deep learning. Let's get started. Today I'm going to discuss about what data set I selected, how I did the annotations, what algorithms I use, and we're going to compare the results. Now, what is the object detection? Object detection is a computer technology related to computer vision and image processing that deals with detecting objects of a certain classes in digital images and the videos. What are the uses? The object detection is widely used in a computer vision tasks such as image annotations, vehicle counting, facial detection, pedestrian counting, and many more. We also use it in a tracking different objects. Suppose an autonomous car is on the track, then it can detect a real car moving by its side and the pedestrian crossing the road. These are the real tracking algorithms that we will be able to use after training our models for such classifications. Now, let's look at what dataset I selected and what information they carry. I selected the new scenes dataset. It is one of the child branch of autonomous vehicle company called Motional. Motional is shooting for L4 and L5 autonomous systems approved by the government, which is for which we do not need any human interactions to drive a car from one place to another. And in that particular technology, we definitely need a lot of object detections. They keep the dataset open source so that any student can use it and have a hands-on experience, but that's not for the commercial purposes. That dataset contains a different map generated by the LiDAR point clouds and different images. But over here, we only gonna look at the images captured by different cameras. That's how the car looks like, and that's how the sensor positions looks like. As you can see, we have 6 cameras and we got all the pictures from these 6 cameras, and we gonna annotate them to put it into the network and to do the classification on it. Now, how did I do the self annotations and how did I generate the data sets? Let's look at it. First of all, RoboFlow. RoboFlow is an open source platform to annotate your own data set for small projects and commercial users. Now, why to annotate, right? Like what is the need to annotate those? The thing is, we have different objects in a one photo frame. So this particular algorithm will not know what to feed in this particular network. That's why if we annotate an object, then it will know like that particular image I have to feed for my training purposes. That's why it's one of the major key point for generating the data sets. Now let's look at the live demo of the RoboFlow. But first of all, let's look at the new scenes and how we can download the dataset. As you can visit the new scenes powered by the Motional, we can go to download section and there are a lot of different dataset available. I did download the full dataset mini version, which is of almost 4 GB, through which I just extracted only images and put it into our RoboFlow. Now, over here, I included 1087 pictures for our input. I did 3196 annotations, almost 3 annotations per image. Average image size is 1.4 MB, and the median image ratio is 600 by 900. Now, let's look at our classes. We have like 4 classes. Each class has their own number, which is we have like 1400 cars, 700 pedestrians, so on and so forth. As you can see, we have under representation class over here. So what I did was I went to the Google and downloaded all the pictures of the heavy vehicles and the workers and including this particular annotation so that we will have at least enough number of annotations to train the particular model so that our model will not get just biased to the pedestrians in the cars. Apart from that, we have a lot of insights of this particular data set that we annotate. This is one of the cool features which shows the annotation heat map. It shows where did I annotate in the whole my annotation process for the heavy vehicles. For the cars, which is basically on the road, that's why this is lower below, and the pedestrians, those who were standing, that's why it's like straight. It's pretty cool. Now, let's look at our data set. Our data set exactly look like this. The thing is, all these images that you can see on top, I included them from the internet. That's why they are very different from others. But let's look at the image dataset from the new scenes that I imported. These are the car and these are the annotation that I did by myself. And they have all the information gathered over here in our raw data. That's how, as we're gonna call the API from this particular platform to our network, it will know exactly what square or what image that particular network need to include it in its feed forward network for the neural network training. We can go through some different pictures just like this, pedestrians and cars. So that's how I annotate car, pedestrians and pedestrians, something like that. So that's what basically annotation I did. It took almost like 18 hours for me because it's like too much annotations. Let's go back to our presentation. Now, the first model that I implemented is a YOLOv5. YOLOv5 contains the backbone, the neck as a PA net, and a header as a YOLO layer. As the backbone, it uses CSP darknet. What is CSP darknet? CSP darknet is one of the backbone that fetches the images from the, or take the images and give it to the next layer, which will convert it into bottom up layer, which is PANnet. PANnet contains the input from the bottleneck and bottleneck bottom up process and connection of the bottleneck CSP from the previous network. The thing to do combination over here is we want more features. That's the only reason we are connecting from and following the bottom up and the top down approaches. But at the end, we will get the YOLO layers, which is our 3 different layers and 3 different headers, so that we can get and detect very small objects from the top layer, very bigger object from the bottom layer, and medium object from the middle layer. Now we're going to discuss about what are the FPNs and PANs, and we're going to learn what is this portion looks like and why they do that. As you can see over here, it uses the backbone, then by FPN layer, and at the end, it gives the output with hidden layers connected with it. And at the end, it gives final output. The thing is, as you can follow over here, the picture as an input, it goes from the bottom up process. And on the second level, it gives from top to down. And it also congregate and connected with a 1x1 convolution neural network for each layer. It keeps the same process and does the third layer. Why we need to do this, like top down, bottom up, and even before like bottom up? The thing is, after doing so much complex calculation and making this particular network, we will get different networks or layers that focuses on different size of the images and the objects lie on that particular layer. So bottom layer is good for bigger objects and the top layer is good for smaller objects. The more layer you have, the more feature extraction you have, just like this, we will have a good hidden layer out input, and we can, after that particular process, we can have the classification and regression header for boundary boxes and object classification. Now, let's look at YOLOv4. Just because we implemented ScaledYOLOv4, we need to understand what exactly YOLOv4 is. Just like previous, we have the input, we follow the backbone, which is bottom up. We feed forward that particular layer and connect it with our any NAC, which we can select as FPN, PAN, by FPN. And at the end, the dense layer that we get, it has a different size of the objects. And again, as like mentioned before, classification header and the regression header for our boundary boxes. We have a lot of option to select from here. Like backbone, we can use RESTnet, EfficientNet, and CSP darknet. Just like that, for the denseNet and the sparse prediction, we have a lot of option to select from, and we can do a combination of each other and make our own custom network. That's our YOLOv4. What is new in a YOLOv5 and YOLOv4? The thing is, YOLOv4 implementation and YOLOv5 implementation, and we're going to compare those differences later on. But let's learn what is ScaledYOLOv4. Just like previously, YOLOv4, we can implement ScaledYOLOv4 with more depth and more extraction of the feature. That's the main reason that ScaledYOLOv4 is better than ScaledYOLOv4 is better than YOLOv4. On top of it, YOLOv4 was implemented in a C and darknet, but ScaledYOLOv4 was implemented in the PyTorch. Now, as we know the basics of these particular models and their structures, let's compare our models. Over here, our all models contains the same category or almost same accuracy and fall into the same place. As we go to the left, it gives YOLO V1, V2, and V3 gives good speed, but not so good accuracy. Over here, the precision and recall call from the ScaledYOLOv4 shows the pedestrian, the area under the curve for the pedestrian is 56. And for YOLOv5, it says 50%. Just by looking at the number, we can say that the classification score for the ScaledYOLOv4 objects are better than YOLOv5. And these are the results. This is the result from the ScaledYOLOv4, and it detects this particular pedestrian. But in a YOLOv5, we are not able to detect these pedestrians. Now, what are the major differences? So YOLOv4 was implemented in a darknet framework in a C, but YOLOv5 is implemented in the PyTorch framework, which make the loading of this particular images very easy and 10 times faster. YOLOv4 uses configuration file, but ScaledYOLOv4 uses exactly same configuration, exactly same file as YOLOv5. The thing is, they both are implemented in a PyTorch. ScaledYOLOv4 also implemented in a PyTorch, and they still can use the YAML file used by the YOLOv5 for the data loading. But ScaledYOLOv4 gives us the efficiently scaling the network design than YOLOv5. Now let's look at the code and my structure. So the thing is, I will be sharing this particular folder with the professor and the students so that they can look at it. The thing is, you can go to YOLOv5 over here, and you can find the results generated by this particular algorithm. You will find all kind of graphs over here. You will find all the test results or the inferences, you can say, over here, just like this. And as we have not much time, we're still just gonna go through quickly through our code. So we install the dependencies for YOLOv5. We imported the libraries. We export our data as a YOLOv5 PyTorch, which will be the same for the ScaledYOLOv4, like I mentioned before, the same YAML file. This is the structure that we want to take care. This is the API from which we are following the data set. That's what I wanted to tell you. It has the same 4 classes. This is the structure of the YOLOv5. And let's just jump to the output. As you can see, YOLOv5 gives the operation that we can do and see our result just like this. But Over in a scale yellow v4, we are not getting those results. We are getting this graph only. After that, these are the inferences and the batch. And at the end, all the output is saved in this particular file. So go ahead and look at it. And that's all for today. Thank you guys.